Thank you, and thank you especially to the organisers for putting up with all of my technological issues. So now they've been resolved, I'll be talking about an update on the sum product problem, and as has been said, this is joint work with Misha Rudnev. Okay, so I'm certain that you've all heard of the sum product problem, but maybe it's not at the forefront of your mind. So the sum product problem takes a set A. So this set for us is going to live inside the real numbers. It's going to be a finite set, and that's the only thing we'll impose on it. And from this set, we can create two further sets, two auxiliary sets, the sum set, so the set of all possible sums we could have made from pairs of elements in that set, and also the product set, AA, which is a set of all products we could have made with all pairs of elements in that set. So it's a conjecture published by Erdős and Szemerédi, although Malnathanson tells me that it was thought of by Erdős significantly earlier, which is to say that given any finite set A, one of these two auxiliary sets, so one of the sum set or one of the product set, should be large. And by large, it actually almost as large as possible. So if the size of our set is, speak of it as A, then there are, A plus 1 choose 2 possible pairs that we could put into this sum set, which means that the biggest thing that A plus A could be is A squared. And it's a minus little o of one term to account for some log factors, which are really consequences of number theory. And throughout this talk, when I have my exponent a little over one term, what I'm hiding is factors of log A, constants, and anything that's a smaller power of A. All right. So what I'd like you to remind you of is that the sum set of the product set should be at least A squared, so the power, the exponent of 2 is what we're aiming for here. And I said that Misha and I have got a new result towards this. But a new result without any context is meaningless, so let me put some context to this new result. Okay, so this is a chart to show what progress has been made. And so we've got a timeline going on the horizontal axis, and the exponent is climbing up the vertical axis. So there's kind of two things that I'd like you to notice here. So the first thing is that, I said that for the exponent, we're aiming to get to 2. And currently, this chart goes up to 1.5. And not only does it stop very far beneath 2, it also stops very far beneath 1.5. So you can have the optimistic or the pessimistic point of view from this. So we're still very far away from knowing the true answer, but also there's a lot of interesting new ideas that are still to come. So the second thing that I wanted to point out were that there's kind of two major leaps in the chart. And these are symbolized by the bigger red dots here and here. And they represent two new ideas within this problem. Okay, so this first jump is a result of Aix, and Aix introduced the Szemerédi-Trotter theorem into the sum product problem. So if you've never heard of it, the Szemerédi-Trotter theorem is a theorem about points and lines. It's saying that if you've got a finite set of points and a finite set of lines, then you can count the maximum number of times that number of pairs of points in a line so that the point lies in the line. So somehow Aix manipulated this statement about points and lines, about instance geometry, into a very elegant solution of this sum product problem. So Aix introduced instance geometry, and this second improvement after Aix is also a consequence of instance geometry. But the second point that I'd like to highlight is actually the emoji in which he removed instance geometry from the problem again. So he removed instance geometry, but he kept the argument of his sum product exponent as a very geometrical argument. So it's really proof by picture. And this gave a exponent of 4/3. So 4/3 is kind of actually not quite the threshold because it's been beaten, but it's the main number of the threshold. So let me say that in a few more words. After Shkredov's 4/3 exponent, came an argument of Konyagin and Shkredov, and they got 4/3 plus c, and their c was maybe 4/3 plus 1/10,000. And every subsequent improvement, so ours included, is really a refinement of Konyagin and Shkredov's argument, right up until this penultimate yellow dot here, which is the result of George Shkredov in 2018. And then this allows me to introduce the context of the new result of Misha and myself, which is this final dot here. So clearly it's an improvement. I also like me telling you about it, but in context, it's a very minuscule numerically improvement. However, please don't be disheartened. I think that this is a very interesting result. It's a very interesting result because what we tried to do, the reason why we started this project is, we took Konyagin and Shkredov's argument and we tried to understand what was going on. We tried to understand what was going on very simple, very pedestrian terms. And the result of this is that we've got an argument which, to some extent, is elementary. That's not to say it's not complicated, but it really gets into the heart of what Konyagin and Shkredov have done. So Konyagin and Shkredov, they use many tools, a lot of powerful machinery, whereas Misha and I were able to strip away many layers of complication and really get to the heart of their argument. All right. So what is our result? Our result is this as follows. So given a finite set A in real numbers, we know that the maximum of either the product set or the sum set is at least a to the 4/3, so Shkredov's exponent, plus 2/1167. And then there's some additional constant factors, some log A factors floating around, which I'll ignore. So for context, we've got roughly 2/1000 as our improvement on Shkredov's exponent, whereas George Shkredov, the previous result, had 1/1000 with some creative rounding here. All right, so our new result. Again, let me tell you about the new result. So our new result follows two types of arguments. And the first one is as follows. So the first one is saying that if our set A is multiplicatively structured, we extract some information on the sum set. And morally, this is kind of what Shkredov did in his argument as well, in a different form, of course. What do I mean by multiplicatively structured? When I say multiplicatively structured, I'm saying that if I were to take any element of A, is to say that for my set A, I can associate two auxiliary sets, so a set R, so that any element of my favorite set, the set of interest A, can be written as a product of an element of Q times an element of R in at least T different ways. So I'm going to say that A is multiplicatively structured, the number of representations of any element of A, and I'm looking at representations as a product of an element of R, is at least T. So in this game of multiplicatively structured that we play, what we'd like this number T to be very large. We'd like this to be as large as possible. And we can capture A multiplicatively in some quite small sets. So we like the size of Q and the size of R to be small, and we'd like T to be large. Okay, that's all very well, but we need a second part. So if A is multiplicatively structured, we're fine. The second thing to show is that every A is multiplicatively structured. Okay, so as it stands, that's quite a strong statement, particularly technical definition of what I've said multiplicative structure is. But let me show you that that's maybe not so surprising. So for example, let's take any element of A, and in fact, let's take two elements of our set A and B. And I can write A always as A times B over B, always assuming that B is not 0. And well, for any element A, there's however many, the size of capital of our set many choices of B. So in the notation of this first point, that's saying that the representation's number of an element A as a product from the product set and its product of the inverses is at least A. So in this sense, every set is multiplicatively structured. And I've said that this is trivial. And it's trivial because we didn't have to think about it. So it's trivial in the sense that we kind of get this for free. Not trivial in the sense that this is actually quite powerful, this observation. This particularly if you know, for example, that you've got this is a very good tool, very good. Okay, so where was I? I was saying that every set A is multiplicatively structured. And I said that, well, actually, this is a lie, what I've been saying in the second point. What we actually show is that every set A has a subset, and this subset has multiplicative structure in a very specific sense. All right, so my next slide is really only relevant if you have studied this before, if you're very familiar with the previous results, and if not, please take a 30-second nap. So how do these two sections of our argument build on previous results? So the first bit, if A is multiplicatively information on the sum set, and this in particular replaces the argument of Konyagin and Shkredov using semi-ready tractor sets. It replaces the notation of D plus of A, and the actual argument itself is a form of Shkredov's operator method. So Shkredov's operator method is it's a lovely use of linear algebra and eigenvalues, and this is just saying that, well, we can get different results if we use a slightly different method. And the second point, the fact that every A is multiplicatively structured, this uses the bunches argument or the clustering argument of Konyagin and Shkredov. And this in turn builds on Shonimoshi's work, which is bounding the subset by the multiplicative energy. So if in your mind you've got that picture in Shonimoshi's work, this is really the extension. All right, so if you took your nap, now's a good time to come back. And before I continue with the rest of this talk, I'll just go for a quick pause in case there are any questions on what I've said so far. Nope, perfect. Okay, so the first part of what I said in the argument was that if we've got multiplicative structure, we get some additive information on our set. So let's just recap. What do I mean by multiplicative structure? By multiplicative structure, I mean that every element in A has got at least T solutions to this equation, A equals Q times R, for some given sets Q and R. Out of interest, these will be finite sets that live in the reals. And we also need some restriction on the cardinality of Q and R in comparison to the size of A. Okay, what this means is that the sum set to the power 19 times this set Q, the cardinality of that to the 22, times R to the 22 is at least A to the power 41 plus some log factors, multiplied by this number T to the 33. Okay, these are not inspiring exponents, so please forget them. But I wanted to show you what this result looks like. Multiplicative structure gives us additive information. Why is that the case? So Urias in his talk, he mentioned the idea of additive energy. The additive energy between two sets, A and B, which I'll denote as E sub K, is the sum over elements of the different set A minus B times the representation function to the power K. So it's somehow the kth moment of the representation function of the different set. Okay, so that's some multiplicative structure. And I claim that this is going to give us good energy bounds for this additive energy. And why is this? So what we'll do, we'll look at part of the support of this function. And we'll introduce a parameter tau, and let's look at x tau to be the set of elements in this different set for which the representation of an element in this is at least tau. So we're looking at the tau-rich element of A minus B. Okay, so now we've defined this set x tau. Well, we've got firstly the trivial inequality, which is the definition. We know that x tau times tau is at least the number of, is less than the number of solutions to the equation x equals A minus B, with all elements living in the various sets. But we also know something in addition. We know that our set A has got multiplicative structure. So we can put that in. We know that every element A looks like Q times R, so we'll do that. But it looks like Q times R at least T ways. So we have to divide by this factor of T as well. Okay, so now looking at this equation, we seem to have translated it from a problem of 3 variables to a problem of 4 variables, and by all logic, this should be harder to bound. However, you don't need to look too hard at this equation to recognize it as the equation of a point living in a line. So in particular, the points, say r comma x, living in the line with gradient q and y-intercept minus b. And this is great news for us because we've got the Semeredi-Trotter theorem, which I mentioned earlier, which is a way of counting the number of times a point lies in a line. So then in the Semeredi-Trotter theorem, we'll tidy up. And this means that we've got good by which I mean better than trivial energy estimates when we're looking at eighth energy for k anywhere between 0 and 3. And the closer k is to 3, the better our energy estimates are. Okay, so how does this help us with this theorem that I've stated again here? Well, let me show you how we prove this theorem in a very specific, very toy model. So in our model, let's look at the difference sets, A minus A. And we'll assume that every difference in our difference set has got exactly the same number of differences. So it's got exactly delta differences. And if this were true, delta would be A squared over the size of the difference set. And then what we're going to do, we're going to count the number of solutions, so A, B, and C, all elements of A, to the equation A minus B equals A plus C minus B. So on the one hand, this is quite a stupid equation. We've got, we've added and subtracted the same thing. So what this means, though, is that we've got quite a lot of solutions. So if we fix any A minus B inside our different set, there's delta ways that we could have done this. And we can choose C to be anything living in A, which means that on the one hand, we've got at least delta times A minus A times A solutions. So finding the lower bound to the number of solutions of this equation was very nice, very easy. The hard work's obviously in the upper bound. So what we'll do, we'll partition our solutions of this equation into equivalent classes. And we'll say that if we've got 2 solutions, then they're the same in this equivalence if, say, the left-hand side of one solution is the same as the left-hand side of another. And this term is the same as, A plus T plus B minus T. Okay, so we'll then count the number of solutions by these equivalence classes. We'll use our favorite trick in additive combinatorics. We'll use the Cauchy-Schwarz inequality. And this will tell us that the number of solutions is bounded above by a third energy of A, and this rather complicated looking expression, which characterizes the number of solutions to D equals X minus Y, where X and Y are elements of the sum set. Okay, so this is just one application of Cauchy-Schwarz. So on the one hand, we've got this E3 of A. And what I've just hopefully convinced you of the previous slide is that because A has got multiplicative structure, we are very good at bounding this using the Sem-Reddy-Trotter theorem. Let's take a moment to look at this slightly more complicated expression. I've renamed it to be S and got rid of the square root as well. This is the torque, so let's introduce another toy model. And let's assume that every element of our, well, this X here, every X that we chose here was popular. So popular in the same sense that Yuri has used previously, saying that every element X can be represented, every element X can be represented as A plus A in at least half times the average number of ways. Okay, so what does this mean? This means that every time we see an X in the contributing to S, we can replace X by A plus B. We could have done this many ways, so we've got to account for that with this multiplicative factor out the front here. And now we've reduced this complicated expression, again involving 3 variables, to a more complicated expression involving 4 variables. And again, going from 3 to 4 variables is somehow helping us because, well, we can write the number of solutions to D equals A plus B minus Y. That's the number of solutions to D minus B equals A minus Y, which when we can rewrite this in the representation formulation, and this Y here should in fact be an X, so I apologize for that. And then we've now got a sum over 2 terms. We don't understand how they interact together, so we'll use a holder to separate these terms into energy estimates. So then what we're left with is estimating the 3/2 energy of D and A, and the third energy of A and A plus A. So again, remember that we're very good at estimating the energy because we've got this information of A, and we're good at doing that as long as the subscript here is at most 3. So in both of these cases, using this Sem-Reddy-Trotter trick from earlier, we can estimate them well. And then tidying up this argument, doing some bookkeeping, proves the theorem. So it proves the theorem under these toy model assumptions. So let's remind you what these toy model assumptions were. So the first one is saying that every element of the different set has got roughly the same number of representations. This toy model isn't too hard to remove, and we remove it using the dyadic pigeonhole principle at a cost of a logarithmic factor. The second toy model, though, is saying that every element of the sum set is popular. It's harder to remove, and it's more interesting how we do it. So I won't go into the details, but let me whet your appetites and say that we have a new regularization lemma, which allows us to get rid of this model. And because what we need not only that this X is popular, but it's also popular with an element, so X equals A plus C, but we also need that this A is somehow contributes to the support of the additive energy here. All right. So I think, no, that's not all I wanted to say. So what did I say here? I said that if we've got multiplicative structure, we get additive information. But actually, the only thing that we use is that the only reason that we needed this multiplicative structure is to get a grasp on the additive energy of A with some other set. But it turns out there's actually whole families for which we can estimate this energy well, and one of them is convex sets. A set A is convex if we order the elements from smallest to biggest, that the difference between the consecutive terms keeps on growing. And for convex sets, we can estimate the additive energy very well using the same Sem-Reddy-Trotter trick. So if we put that numerology into our technique, we get the bound that the sum set for a convex set A is at least the size of A to the 30/19 up to some logarithmic and constant factors. And this beats the previous best bound of Olmazov. So convex families are one such family for which we can estimate the additive energy very well. And let me just say that there's another family for which we can do this, which is a family called totally distinct consecutive different sets, which was introduced in Cirm. And again, for this family of sets, we can estimate the energy well, and so we have the same exponent. Okay, so that concludes what I wanted to say about the concept that if we've got multiplicative structure, then we can get additive information. And then the second part that I'd like to talk about is to say that if we've got a set, every set has got a multiplicatively structured subset. So for the rest of the talk, what I'll do, I'll describe how to get this subset. I'll give a vague argument as to why it's a good subset to choose. But I won't really go into the quantitative details of this argument. Okay, so part 2, every set A has got a multiplicatively structured subset. So let's find this subset. So first what we're going to do, we're going to look at our set A, and we're going to make it into a point set. So A cross A, and we're going to this point set with lines through the origin. And this is a torque, so let's assume the toy case, and we'll assume that the same number of points fall on each line. I may call this number of points how. Okay, so then what we're going to do, we're going to look at each abscissa, x0, so we're just going to go along the horizontal axis, and we're going to look at each vertical line through any point in A, and we're going to count the number of points of A cross A lying on this vertical line. So we'll do this for every possible abscissa in A, and there'll be one line, maybe there'll be several, but there'll be at least one abscissa which is going to give us the most number of points on this vertical line. So let's say that this is x0. So let's say that this vertical line is the one with the most number of points on it. Okay, there's not very much left that we can do now, except project it to the y-axis. So we knew that x0 in A, we know that all of these green points are in A cross A, which means that when we project this line or the point on this line to the y-axis, we're going to get a set of values, say B in A. So this set B that I defined here is a subset that we'll use. And I claim that this subset has got multiplicative structure. So let me try and convince you of this in a very informal way. Why is B special? So let's look at any element of this subset that we've found, say B, and let's say that B, we know that it lives on, well, a line through the origin that passes through this x0. So we can say that B is some lambda times x0, which means that we can write B equals A1 over A2 times x0 in at least tau different ways, where tau is the number of points per line. Because there are tau different ways to write this lambda. In particular, we can do our favorite math trick of multiplying by 1 to say that, well, seeing as B equals A1 over A2 has got lots of solutions, in fact, we can multiply by 1 to see that B equals A1 over times C over A2 times C times x0 has got even more solutions. And how many solutions? And I think what we'll use now is the Katskuster trick. So let's, how many solutions does B have? B has at least as many solutions as there are different denominators. So we're now going to ask ourselves, how many different denominators are there? So every denominator here looks like A2 times C. Every A2 lives inside A, but it also lives inside lambda to the minus 1 A. Which means that A2 and C times C lives inside AA, but it also lives inside this second set, A lambda times A. Okay, so what data does this give us? So this argument shows us that for every B that we started with here, so every element B of our subset, we can write B as a element of, well, this numerator over this denominator in at least A times A lambda ways. So this is the data that we have. And then, of course, the rest of the argument is to show that A times A lambda is, well, it's big and independent of this value lambda. And this is then, if we have this data, this is good news for us because this is the theorem that we'd like to plug this result into. Okay, and that's really all I want to say about how to find the additive subset. Yes, and the other thing that I wanted to highlight was, in fact, our argument is very elementary. So it's not using high-level combinatorics. It's not using, for example, the Balog-Semerani-Gauss theorem. It really is using very pedestrian tools. However, the sum product problem generates lots of research because there's lots to improve every result that appears, every new idea that appears. So what I wanted to do today, I wanted to end my talk with saying, well, how does our argument, how could it be improved? And for this, let me just recall this theorem here, which is saying that if we've got multiplicative information, then we've got A plus A to the 19 times Q to the 22 times R to the 22, A to the 41 times T to the 33. So this was a theme of multiplicative structure gives us additive information. So this theorem, which I've just repeated, is very unlikely to be the strongest form of this statement. This A plus A to the 19, Q to the 22, 41, 33, these are unlikely to be the best exponents that we can get from. So that gives us hope that this part of the theorem could be improved. And let's remember how we got to this statement. So we got to this statement by looking at A minus C is A plus C and B plus C. And here we chose to count all of the solutions where each of the solutions lives inside A. But it's not necessary for C, for example, to live inside A. Perhaps there's a better subset of A, or maybe even a superset of A, or even maybe a different set completely where C could live. And maybe this could help us in some way. So the first part of our argument can certainly be improved. The second part of our argument, every set has got a multiplicatively structured subset. I certainly wouldn't rule out the fact that this part of the argument can be improved. It can be improved in several ways. The set B that we found, maybe it's got more multiplicative structure than we can quantitatively show. And so what this would correspond to is that this set A times A lambda would be bigger than we show it is. But perhaps actually this is the wrong set to work with completely. Perhaps there's a better subset of A which has got even stronger multiplicative structure. So it could be better in two ways. It could be a bigger subset, or it could be a smaller subset but with more powerful structure. So I suppose this slide is really saying it's over to you now. Misha and I were able to show that the maximum of the product set and the sum set is at least A to the 4/3 plus 2 over 1,167. But maybe the next time that this comes, someone else will be talking and someone else will have a much better number and a different argument. And I look forward to that talk. Thank you.